Just a minute. This is the actual transformer. Then we had kept some winding. Then you are having the source. Then you are having resistor. Then for this, we have drawn the phasor diagram where E1 is the induced EMF that is considered as a voltage drop. Then we saw IC, that is the core loss component. Then we saw that I magnetization component. Then we saw the resultant current. Okay, this is flux that is creating the flux. Then I magnetization part. We saw this current. Then after that, we included this resistor voltage drop across this resistor. That current will be in phase with this IM. So that voltage will be in phase with this IM. So we have write this yesterday, and we have written IM. This is V. This is the source voltage V. This is what we have done yesterday. After that, I was discussing. We were discussing something about including an inductor here, which is for the representation of the leakage flux. So after that, the circuit will become like this. Now this is voltage E1. Then this is the voltage across the inductor. This is the voltage across the resistor, and this is the source voltage. Now the source voltage, that is V is equal to VR plus VL plus E1. If you apply KVL for this particular circuit, you will be getting VR plus VL plus E1. So already we have VR plus E1 here. Now we wanted to rewrite it. So now we are taking E1 like this, and we are having IC here already. Then we are having I5. Then we are having, just a minute. So our I magnetization current, that is the resultant current, was here. So now we are having two components. One is this voltage across the resistor, and another one is the voltage across the inductor. Now when you are drawing the, am I audible?
Yes, sir.
So the voltage across the resistor will be in phase with the current. So you draw it parallelly, so that this we have already done. So now the voltage and the current are 90-degree phase shifted for the inductor. So when you are talking in terms of inductor, the current flowing through this is IM. The current flowing through this is IM. Then that current will be lagging in voltage, lagging with respect to this voltage by 90 degree. So in that case, you can draw this diagram. So this is the inductor voltage. That inductor voltage is 90 degree ahead with respect to the current. So here, this is the current for this. This is the voltage across the resistor. Both are in phase. So we have drawn it parallelly. So after we drawn that parallelly, the inductor voltage is 90 degree ahead with respect to that current, so we have drawn it 90-degree like this. Then this is the voltage across the inductor. Then you draw the overall voltage. This is the resultant voltage, because the resultant voltage is Vs or V. The resultant voltage is given by Vs is equal to Vr plus VL plus E1. E1 is the induced voltage as a voltage drop. So this circuit can be drawn like, written like this. This circuit can be drawn like this. This is the KVL equation for that. So this is given by the vector addition of this particular path. So this is E1, then followed by the voltage across the resistor, then followed by the voltage across the inductor. Then the sum of these voltages will be giving the source voltage. Now this source voltage is leading the current by certain angle. You know that theta we consider, you know that it is behaving like an inductive circuit. So if it is behaving like an inductive circuit, the resultant voltage will be leading the current by an angle theta, some angle. The same thing is followed here. Now this is for the basic transformer. In this we'll be talking about the phasor diagram later for the complete transformer. But before that, how to start or how to create an equivalent circuit from the basic understanding of our transformer. Okay, so that we will be seeing it now. So we will be seeing the concept. Phasor diagram we will see it later. So consider this. Here we are going to consider the transformer under loaded condition. Till now we had considered the transformer in an unloaded condition, or without load we had considered. Now we will be considering the transformer with load. Okay, so now with this what we will be having is, so now we are having a transformer which is like this. Now we are going to have load also. Okay, so what is this impact of the load that we are going to see? So now we are having a load. Okay, so now we already discussed that there is some copper loss and there is some core loss. So for copper loss we are including this resistor. Then for the leakage flux we are including this inductor. So this is for the primary side winding. Okay, this is the leakage flux on the primary side. Okay, so we'll draw this leakage flux later. So we'll be just including the resistor. This is for the copper loss on the primary winding. Similarly, there is a copper loss on the secondary winding. To represent that, I am including a resistor here. Okay, then you are having the load. Then you are having the source here. So now the current is flowing through this. So the current is taking this direction. Then if the current is taking this direction, then flux direction will be like coming out of that. Okay, now I'm mentioning the dot line, so dot polarity here. That is dot. That dot represents that here I'm going to get the positive polarity, and here I'm going to get the negative polarity. So the current is coming out of the positive polarity for the secondary side. The current is coming into the dot terminal for this primary side. Now here there is going to be current that is going to flow through this path. Okay, so the current will be flowing through this direction. So on the primary side, because of this current, there is some flux. That flux is going to be having two parts. One is leakage flux, which is going to link only one winding, that is primary winding, that is not linking the secondary winding. Okay, so this is a leakage flux. Then there is another flux which is linking both the primary and secondary, that is mutual flux. This is phi L1. So similarly, if current is passing through the secondary winding of the transformer, then in the transformer there is some current flow. Because of that current flow will induce some flux, establish some flux. So that flux will also having leakage flux. Okay, this will establish flux in such a way that opposes the actual flux. The actual flux direction is from top to bottom. So if this current is establishing some flux, then that flux direction will be opposite to the actual flux. Okay, because here the cause for this current is this flux. So as we discussed yesterday, Lenz's law says that if there is some EMF induced across this terminal, then that EMF induced will be allowing some current to flow on the secondary side if the circuit is closed. If the circuit is closed, then there is going to be some current flow. If that current flow, because of that current flow, if some flux is established, that flux will be opposing the cause. Here, the response is the flux which is established by the current flowing in the secondary of the transformer. The secondary of the transformer, we are having some current flow, that is I2. That current is establishing some flux. That flux, that is flux which is established by the secondary current, that flux will be opposing the mutual flux. Here mutual flux is the cause and this secondary flux is the response. So the secondary flux is the response that will oppose the cause, that is given by the Lenz law. So now if this current is establishing the flux, that will be opposing this mutual flux. Okay, so now, okay, now this is this side. So this is a mutual flux that is in this side. Then this is establishing some flux that is opposite to the mutual flux. Now the primary turns are having a leakage flux and secondary turn is also having a leakage flux. So this leakage flux, we wanted to remove it and we wanted to include in the circuit. So for that only we have included here, we had included an inductor on primary side yesterday, right? We had included an inductor on the primary side yesterday. So we'll be completing that. So now what we are doing, we are removing the leakage flux and we are going to include in the circuit. Okay, so now the EMF induced, that is E1, that is given only by E is equal to N into d phi by dt. This d phi by dt is only the mutual flux. So we are neglecting the leakage flux here itself. So we don't have leakage flux part in the induced EMF here, but there is some leakage flux that is going to induce some EMF. So in order to represent that, we are going to represent that as an inductor that is going to be in the series. Okay, so now already we are having a resistor, we are having the source here. So what we did, we have removed the leakage flux and we are representing that as an inductor here, because that is going to reflect as a voltage drop voltage. So that voltage is going to be represented in this series. Why it is connected in series? Yesterday itself we have discussed. So if the current is increasing, then the flux also will be increasing. The hysteresis loop will not be followed by this leakage flux. The hysteresis loop will not be followed by this leakage flux, because only some part of the leakage flux is linking the core. So only in the core you can get hysteresis path or hysteresis loop. Here most of the flux is outside the magnetic core. So because of that, the hysteresis loop will not be followed by that. So when the hysteresis loop is not followed by that, when you are increasing the intensity, magnetic field intensity, then the flux density will also increase. If you are decreasing the intensity, then the flux density will also decrease. So it will be like a linear relation. So if you want to represent such a thing, you have to connect it in the series parameter as a inductor. Why we are mentioning it as an inductor? Because the magnetic flux can be represented as an inductor. If it is an electric field, we have to represent it as a capacitor. Okay, because this will store the energy in terms of magnetic field. So we are going to represent it in terms of inductor. So now this is for the primary side. Similarly, for the secondary side, we are going to include the inductor instead of the leakage flux. So other than that, once you remove the leakage flux, we are having only the mutual flux now. We have removed the leakage flux, so we are having only the mutual flux now. Now this is the overall circuit. In this circuit, we are directly represented the copper loss and the leakage flux in the series winding of this primary and secondary. Now we have to include something related to the core loss and the magnetization part. Core loss and the magnetization part. Okay. So now in order to represent the core loss and magnetization part, you can see here, we are going to represent this in terms of shunt element like this. Okay. Now what we are doing, we are going to represent that shunt part. Okay, so this is the transformer, and in this we are having a primary winding, and we are having a resistor and an inductor, and this is this, and inductor and resistor. Then you are having the load. This is the mutual flux. Now we want to include the shunt element. Okay, this shunt element is going to represent the core loss and the flux which is established on the mutual flux. So now I'm having a resistor here, that is RC, and this is XM. So this XM is the part which is going to establish the magnetization characteristics of the transformer. Why we are drawing it in the shunt is, so if some current flows through this path, then whichever is here, then this, I told that this flux which is established by this inductor, that is in phase with the current. Okay, whereas for this inductor, the current and the flux need not to be in phase always. Okay, so if the same current is flowing, then this current and the flux established by this both will be in phase, whereas if it is in the shunt, both need not to be in phase. Now if some current is flowing through this, some current will be divided here and some current will be divided here. So this is the current which is going to give the magnetization overall current, magnetization current. So this magnetization current is going to have two parts. One is going to represent the core loss. One is going to represent the core loss, that is the heat dissipation. That's why in the phasor diagram we have drawn IC here and we have drawn I5 here. So in that we got the overall sum, that is the magnetization current. So the overall current which is flowing inside this is the magnetization current. That current is going to be divided into two parts. One is the current which is going to responsible for the core loss, which is going to be happening in the heat dissipation. So that is going to be represented as the RC. And there is one more part which is responsible for establishing the flux in the magnetic core. So that is called as XM. Okay, so you are having the mutual flux. So for this mutual flux, you are going to have some current. That current is going to be represented here. So this is the current I5. This current is going to responsible for developing this mutual flux. Okay, now we'll be proceeding further. So this is our complete transformer part. And you are having this part. Do you have any doubt in this? This shunt part is responsible for the magnetic flux established and the core loss, and this series part is going to responsible for the copper loss in the system. Now you are having a mutual flux. So now we will be seeing about how the input current changes when there is a need of more current on the load. See, if there is a load, let's consider that initially there was no load. Let's say that initially there was no load, the circuit was open. So because of that, that there is no current which will be flowing through this path. The current flowing through this path will be zero, right? So even when the current flowing in the secondary is zero, the current flowing in the primary will not be equal to zero. Okay, why? Because even if the transformer is not loaded, that means in the secondary side, even if there is no current flowing through the secondary side, that means I is equal to zero on the secondary side when it is in the open circuit, then also some current will be flowing on the primary side. That current is flowing to magnetize the transformer. So that magnetization part and the core loss, here we'll be having XM, and this is, we'll call it as XSC, and this RSC. 1. So there is some current, that is magnetization current. So here, when the secondary is not loaded, when the secondary of the transformer is not carrying any current, then also the primary will be carrying some current. Okay, why that current is there? That current is responsible for establishing the magnetic flux, that is a mutual flux in the magnetic core material. Okay, so now for time being, you can consider that this I1 is equal to Im, because the current flowing through this path is zero. This current, I will be saying what is that, this current is zero as of now. Now this is for the source voltage. Now for no load condition, no load condition means for there is no load at the secondary side, the secondary current is equal to zero, whereas the primary current, that is I1, is not equal to zero, because the transformer need to be magnetized. If the transformer need to be magnetized, then there should be some flux. If there should be some flux, then there should be some current. So that current is taken from this source, then your I1 is having some value and Im is having some value. So at this time, your I1 is equal to Im. The source current is equal to Im. Now, this IB is called as balancing current. This IB is called as balancing current. So now you just think, if I increase the load on the secondary, if I increase the load on the secondary, how the primary knows that there is some requirement of the load? Can anyone think? The question is, if I increase the load on the secondary, means that initially the current flowing through this path is zero. If I add some load, let's say that I am adding some load that is taking 1 ampere. So that 1 ampere current should be flown from the primary side. Of course, that 1 ampere current should be flown from the primary side. So if that is the case, how the transformer primary will be getting to know that there is a requirement of increase in current on the secondary? Can anyone tell me? Can anyone guess why, how the secondary will get to know that primary is requiring, how the primary is getting to know that secondary requires some current?
Flux change in the core.
How the flux will change? You mean that this mutual flux will change?
Sir, if there is voltage difference created
Where voltage difference is created?
in the secondary circuit,
So secondary side voltage is changed, then what will happen?
so then it may be like there is a current requirement.
Make it precise. It's not clear. You would have performed these experiments, right? Some of you would have performed the experiment in physical lab. Okay. So now I wanted to make one point very clear. The magnetization current Im, the magnetization current Im remains constant from no load to full load on the secondary. From no load to full load on the secondary side, this Im will be constant. This Im is responsible for this mutual flux. The Im remains constant from no load to full load. So if the IM is constant, this flux will be constant. Okay. No load means zero current. Full load means rated current of the transformer. Okay. So let me draw it again. And we will be discussing how the primary will be getting to know if there is some increase in load on the secondary side. Okay. So we'll be having a transformer like this. So now in this side also we are having induction. Can you mute yourself? So now there is some shunt element. So that is here. Okay. So this is source voltage. Now some current is flowing. This is I1. That is the current coming out of the source. This is the magnetization current IM. IM is going to be constant from no load to full load. And I2 current is going to change. I2 current is going to change from no load to full load. This is IM is constant. Magnetization current is constant from no load to full load, whereas I2 is going to change from 0 to the rated current. Okay, so that is going to change. Now let us see what will happen when we are having no load to full load current, how the primary gets to know that there is some increase in load. Now this is the mutual flux. Okay, so this is the mutual flux. Now this phi m is constant as long as this Im is constant, right? Now what happens is I2 is equal to 0. Im is having some value. I told that Im is having some value because you need to have the magnetization part. So I1 is having some value. Now I2 changes. I2 is increased because let's say that I am including some load. So initially I2 was 0. If I2 was 0, what is going to happen? There is no current. If I2 is changed to 1 ampere from 0 ampere, then what will happen? The current is flowing through this path is going to increase from 0 to 1. If the current flowing through this path is going to increase from okay, mutual flux is this side, is going to increase from 0 to 1, then what happens is the current is going to flow through this path. If the current is going to flow through this path, already we have discussed that the current will establish some flux. If this current is establishing some flux, I'm just drawing the leakage flux, but this current will also establish some flux. That flux will be opposite to the mutual flux. Okay, so if I draw it clearly, your mutual flux is in this direction, and the flux which is established by this secondary current will be in the opposite direction. Okay, it will be in the opposite direction. Okay, your mutual flux are like this. Your mutual flux is from top to bottom. Then if you see the flux which is established by the secondary current, this is the flux which is established by the secondary current. I told that already. The response will oppose the cause. Here the response is the final secondary flux and the cause is the mutual flux. So the mutual flux will be opposed by the response flux. So now when this is opposing the mutual flux, then you know that the mutual flux need to decrease, because you are having some flux that is opposing the actual cause of it. If it is opposing the actual cause of it, then what happens? Then there was an E1 which is EMF induced on the primary side. Now what happens? Because of the reduction in mutual flux, I told that when the current is increasing, then the opposing flux is increased. Then the opposing flux is increased, then the overall mutual flux is decreasing. When the overall mutual flux is decreasing, then E1 is equal to N1 to, E1 is equal to N into d phi by dt. Then this d phi, this phi is decreased now. When compared to the previous case, this phi is decreased. If this phi is decreased, then the EMF induced will also be decreased. If the EMF induced is also decreased, then here the current flowing through this path is given by Vs minus E1 divided by Z. Okay, the current flowing through this path, you know that if you are having two terminals, by nodal analysis you can consider if you are having V1 here and V2 here, and it is connected by some Z. For AC circuit we need Z, for DC circuit we will be using R. When we are saying nodal analysis, the current flowing through this path is given by V1 minus V2 divided by R. So for AC circuit we have to write it as V1 minus V2 divided by Z. So now the current flowing through this path is given by difference in voltage divided by impedance. So here the difference in voltage is Vs minus E1 divided by Z. So because of the reduction in mutual flux, this E1 flowing through the path is reduced. If the E1 flowing through that path is reduced, then what will happen? The current will increase because the difference in voltage is reduced. So the difference in voltage is increased because the E1 is reduced when compared to the previous case. When E1 is reduced, the current which is coming out of the source, that is I1, that will be increasing. Okay, you understand the sequence. First, the secondary current is increasing. If the secondary current is increasing, okay, if the secondary current is increasing, the flux established by the secondary current is the flux established because of the secondary current is also increasing. If the flux established by the secondary current is increasing, then it will oppose the primary flux which is in this direction, which will oppose the primary flux which is in this direction. So when it is opposing, the overall mutual flux is reducing. If the overall mutual flux is reducing, then the EMF induced on the primary side, that is E1, here in this, the EMF induced is given by d phi by dt. So when the phi is decreasing, then the EMF induced on the primary side is decreasing. When the EMF induced on the primary side is decreasing, then what happens? The current flowing through that path can be given by Vs minus E1 divided by Z. For time being, you forget about this shunt element. Okay, for time being, you forget about the shunt element. So the current flowing through that path can be given by Vs minus E1 divided by Z. So when this E1 is decreasing, the difference between those two elements are increasing because this Vs is constant. This source voltage is constant. If the source voltage is constant and this E1 is decreasing, then the difference in voltage, that is the difference in voltage, is increasing. If the difference in voltage is increasing, divided by the Z will be giving the increase in current. So this is going to reflect in increase in current. So for even for a small change in voltage induced EMF, then there will be a huge current rise. Now this E1 is going to increase. I told that this E1 is going to increase. This E1 is going to increase. I also told that this IM1 is going to be constant. I told that this IM1 is going to be constant from no load to full load. So this IM1 is going to be constant from no load to full load. Then there is only one path where the current can flow, is this path. So this path is called as, is going to carry the balancing current, that is IB. IB is the balancing current. Okay, so what it does, when the load is increasing, then the balancing current will increase in order to compensate the current flowing through this path. So when the balancing current is increasing, then the EMF induced will come back to its previous position. Then the mutual flux will be coming back to the actual position. So now the current is increased. So momentarily the mutual flux will decrease if you are increasing the load. Momentarily, you can understand the point. Momentarily the mutual flux will decrease. When the mutual flux is decreased, then the EMF induced is decreased. If the EMF induced is decreased, then the current flowing through this path is going to increase. If the current flowing through the path, this is IM1 is increasing, then already I told that this I1 is increasing, then IM is constant, as I already told. Then it will reflect in the balancing current. When the balancing current is increased, then EMF will come back to its actual position almost. Then the mutual flux will also increase. Now even for the increased current, the mutual flux will be remain constant. Okay, The point is about the MMF. Okay, we will be seeing the equations later, but the point is about MMF. MMF is given by number of turns into the current. So that is going to be ampere turns, we will call. So that is going to play the role. Okay, so now the balancing current is increasing. When the balancing current is increasing, that will compensate for this E1, and it will make the mutual flux to be constant. So the mutual flux almost remains constant from no load to full load, because this Im will also be constant. Okay, because this Im is responsible for this flux. Now when this Im will vary, okay, this Im will vary when you are changing the voltage. So you can see that these two are connected in parallel almost, except this part. When you are changing the voltage, then this Im will vary. So for our analysis, whatever we have talked, we are considering that the source voltage remains constant. If the source voltage is not remaining constant, then this Im will vary. I told that from no load to full load, this Im is considered as constant. So if I say that the Im is considered as constant, then this Vs is also considered as constant. Okay, for a constant input voltage, the Im remains same or constant from no load to full load. Okay, so now let us consider that the I2 is increased from 1 ampere to 5 ampere. Let's say if I2 is increased from 1 ampere to 5 ampere, then what happens? Now more flux will be there when compared to the previous condition. Then now more flux will be established by the secondary current across this. If more flux established by the secondary current on this secondary winding, then what happened? It will again oppose the mutual flux. If it opposes the mutual flux, then the induced EMF on the primary side will decrease. If the induced EMF on the primary side will decrease, then the current flown by the flow through this source will be increasing. Okay, so that current will be reflecting in the balancing current. So whenever there is some change in load, then that load current will be balanced by this balancing current. So the IB will be related with the I2. There is number of winding, N1 turns will be there and number of turns N2 will be there. So IB will be equal to the ratio, the transformation ratio into I2. That relation we will be seeing. So this is the thing. When secondary current is increasing, it is going to establish some flux that is going to oppose the mutual flux. So because of that, overall mutual flux is decreasing. That is for the momentary purpose. I mean, momentarily it is going to decrease. Then EMF is going to decrease. Then when EMF is decreased, that is across the primary side, that is E1, then the more current will flow from the source. So if more current flow from the source, that will be reflecting in the balancing current. So the balancing current is going to increase the EMF that is induced across the primary. Also, it is going to reflect in the mutual flux, because when the EMF is induced, then it is going to have a constant flux, that is the mutual flux. It will be having a value in such a way that even after more current is flowing, then also the mutual flux remains constant. Okay, so the current, balancing current, is the current which is going to responsible for the changing current on the secondary side. Okay, that is compensated by the balancing current. Did you understand something? If you understand something, we will go for this mathematical equation, how it is related. If you have any doubt, you can ask. If you have any doubt, you can ask. Else, let me proceed further. So now, yeah, do you want to ask something?
No, sir. No, sir. You can continue.
Yeah. So now this is the circuit which I had drawn there. Now this I1 is the current which is coming out as a source. IB is the balancing current. IM is the magnetization current. Then this I2 is the current which is flowing on the secondary side. Now we will be talking in terms of equations. This I1, that is the current which is flowing through this path. I1 is equal to IB plus IM. IB plus IM. So when the secondary current is zero, then this balancing current will also be equal to zero. Balancing current will also be equal to zero. So that time I1 will be equal to IM. That's why I told I1 is equal to Im during the no load condition. Now, the point is that there is some primary MMF. Primary MMF is given by N1 into I1. There is some secondary MMF that is given by N2 into I2. Okay. Now, we have neglected these drops. Once we have neglected these drops, so we will be getting primary MMF is given by N1 and I1. Okay. So now, if you replace this with balancing current, okay, so now we will be directly talking in terms of balancing current, that is N1 into IB. So now this primary MMF that is given by N1 I1, then this is secondary MMF that is N2 into I2. The subtraction of that will be equal to the MMF created by this component, which is related with the mutual flux. Okay, so this is related to the mutual flux. This is related to the primary. This is related to the secondary. The difference in MMF will be equal to the MMF of this particular component. Okay, now that's why this term almost remains constant irrespective of no load to full load. Okay, so here I have mentioned that primary MMF neglecting resistance, reactance drops are very small, so we are neglecting it. Okay, so now when there is a small change in load, then this EB is going to change significantly. That is going to be reflect in the secondary side. So you keep in mind one thing. This is the net EMF. That is the magnetization MMF. They will call this magnetization MMF is almost constant from no load to full load. This magnetization MMF is almost constant from no load to full load. Okay, so this is the primary MMF minus secondary MMF, that will be equal to the magnetization MMF. That magnetization MMF will be constant throughout the time. Now we will be bringing this balancing current in the equation. Okay, just a minute. Okay, so this is the proper explanation. It is written here like how I had said before. So here I told that the source voltage is constant, that they have I have mentioned here. So if there is a small change in E1, that is the induced EMF on the primary side, that is going to reflect on the current. So the current flowing through the part is going to change. If the current flowing through the part is going to change, the current flowing through the N1 turns is going to change. Then we wanted to create, or we have to increase the MMF in such a way that we have to neutralize the demagnetization part. So I did not use the word demagnetization part. So what is the demagnetization is, I told that whenever there is some secondary flux that is going to oppose the mutual flux, if it is opposing the mutual flux, what it is doing, this because of this mutual flux, this complete part is magnetized. Now what we are doing, the secondary side MMF is going to oppose this primary this mutual flux. So because of that, the complete part will be looking like demagnetization part, because it is reducing the magnetization effect by opposing the mutual flux. Since it is opposing the mutual flux, it is like we are going to demagnetize the magnetization part in a slight manner. So because of that, you can see here that we have to do the nullification based on IB into N1. This is the balancing current minus N2 I2 bar. So now, so when the I2 is increasing, then this IB is going to change proportionately in such a way that we are going to get the IB. Okay, so this is what it is saying. This is going to increase if this is also going to increase. If this is going to decrease, then this is also going to decrease. Okay, so this IB is going to represent that when there is some increase in secondary current, then it is going to increase the primary current, that is the balancing current. So why this current is increasing? This current is increasing in such a way that whatever the demagnetization effect created by the secondary current, whatever the demagnetization effect created by the secondary current, that is going to be neutralized by this by this current. That's why it is going to call it as balancing current. So here you are having the secondary. In secondary, you are having the winding. Then you are having this secondary flux, which is like this, and you are having the mutual flux, which is flowing in this direction. So now this is going to oppose the mutual flux. Because of that, there is going to be a demagnetization effect here. There is going to be demagnetization effect here. That demagnetization effect, it's going to be neutralized by the increase in current on the primary side, that is given by the balancing current. So what we are doing for the secondary MMF, we are balancing with the primary MMF in order to avoid or in order to neutralize the demagnetization effect. That's why this is called as balancing current. So if you rewrite this expression, you can see it here. So here this is related with the mutual flux. So it is related here. So now I1 is the primary current. Then this is the secondary current that is related with this turns ratio. What I have done, I have divided by N1 on throughout this equation. If I divide this equation throughout this, then I1 minus N2 divided by N1 into I2 is the IB. Already I told that IB will be proportional to I2 except the transformation ratio. I told this sometime back. So transformation ratio will be equal to A into I2. So that is the same thing they have done here. So here they have got N2 divided by N1 into I2 dash. This is given by balancing current IB. So that they have represented here. Okay, this is IB. Then this will be equal to the magnetization current, that is IM. Okay, so this equations you can go through it. So there is nothing new in this. So here this IB is the balancing current. So this is primary current minus this balancing current that is going to be flown in the primary part. This is the magnetization current. That relation is brought from this part. Okay, so here we have related balancing current with I2 directly. So this I2 dash, we will be seeing what is I2 dash in the later on stage. But from this equation, we have directly brought it I1 minus I2 is equal to IM, or in another way you can write I1 is equal to IM plus I2. Okay, so this is about this magnetization part and its equation. So only one part is remaining for this particular transformer part. One part which is remaining is the equivalent circuit. In the next class, that is from 9 to 10 tomorrow, we will be seeing how we have drawn the equivalent circuit from this. Already you would have performed the experiment, open circuit test and short circuit test and load test of a transformer. Then what we are going to do with the equivalent circuit, and first we will be seeing how to prepare this equivalent circuit or how to make that equivalent circuit. Then from that equivalent circuit, what we are finding out in open circuit test and short circuit test and load test. So with that, this unit will be over. So in next two classes, we'll be completing this transformer part. So main thing is phasor diagram, this equivalent circuit and open circuit test. Phasor diagram also we'll be seeing in the next class. Okay, so in the next class, we'll be seeing how to draw the equivalent circuit and how to draw the phasor diagram for the transformer with loading condition. Okay, it is almost same. There is no much difference with the previous phasor diagram, whichever we have seen. So as of now, that's all. If you want to ask anything, you can ask, else we can end this meeting. Thank you for joining. If you have any doubt,